Okay, let's continue with the next topic. So, Graham's law of diffusion. Now, you know what is diffusion? Diffusion is just mixing of gas molecules by random motion under conditions where molecular collisions occur. And then its opposite is the effusion. Effusion is its opposite. But according to Graham's law, the rate of diffusion depends on the pressure and molecular weight of a gas. So, rate of diffusion is directly proportional to the partial pressure of the gas and inversely proportional to the square root of the molar mass of the gas. So, rate of diffusion, according to Graham's law, rate of diffusion is directly proportional to the partial pressure, and also it's directly proportional to the, inversely proportional to the square root of molar mass of the gas. So, rate of diffusion is directly proportional to P over root M. Rate R. So, we can say that R2 over the ratio R2 over R1 will be equal to P2 over P1 root over M1 over M2 for two gases. So this Graham's law can be applied to diffusion and effusion for both. Okay, let's move on to kinetic theory of gases. So what is kinetic theory of gas? Kinetic theory of gas. Now, it's the assumptions or the postulates of the kinetic molecular theory of gases are also given in your text. You can refer to that. So gases. Now, in this theory, since the gases are randomly moving, even if it's contained inside the vessel, they're always moving. They're always moving. The gases are always moving here and there. So the basic assumption is that during the course of the motion, some of the particles may collide to the walls of the container. Some may come and bounce off. Some molecules may come and bounce off each other. So those are some of the assumptions. Now, the pressure of gases are because of the collision of these atoms or the gas molecules inside the container. Because of the collision, we get the pressure out of gases. That's what the assumption is. And then these assumptions were further unified under molecular distribution of speeds by Maxwell-Boltzmann distribution. Now, what is molecular distribution speed? So, Maxwell-Boltzmann distribution of molecular speeds, the assumptions or the postulates of speed distributions are like, it is based upon probability. How probable, whether there are collisions or repulsions or attraction between the molecules, between the atoms of the gases. It gives the statistical averages of the speed of the whole collection of gas molecules, and the speed of the gaseous molecules may vary from 0 to infinity. So, to understand this, let's look at a distribution graph of Maxwell's Boltzmann law. So these are these are our number of molecules, relative number of molecules, and here we have the speed. So what Maxwell distribution states is that the number of molecules with zero or less speed and infinite speed are very less compared to the bulk of the molecules. So the distribution states that the peak of the molecules will be occupied by the mean probable speed, the number of species that has the mean probable speed, and then a little above will have molecules having the average molecular speed, and those a fraction of the number of molecules will have root mean square speed. But as you increase the temperature, change the color of the pen. As you increase the temperature, the curve flattens out. Which suggests that the number of molecules that has the ability to collide or to give reaction becomes more distributed, or the curve flattens out, so it occurs, the distribution of speed flattens out. It gets distributed throughout the sample. So at higher temperature, fraction of molecules having speed less than a particular value decreases. So this mean probable speed, average speed, root mean square speed, the average velocity comes down as the temperature increases. This is T2, this is our T1. So as T2 is greater than T1. And then, so we know from these observations that our real gases, they deviate from ideal behavior. That means we know that real ideal gas follows this equation. PV is equal to nRT. But real gases, they don't follow this because they deviate. They go away from this equation. It does not follow the pressure volume equation of ideal gas. So therefore, we'll examine what or how real gases behaves. Now, the real gases, they obey or somehow come close to this equation only under two conditions. That is, very low pressure. The pressure has to be very low. And secondly, at high temperature. So under these two conditions, real gases somehow follows PV is equal to nRT. Now, if we plot a graph between the pressure volume and the pressure of a gas, what this means, the pressure is increasing, this means the pressure volume the product is increasing. So for a real gas, it usually is a straight line because it follows this equation. But for lighter gases like hydrogen or helium, it shows positive deviation. It shows positive deviation. This is for helium and hydrogen. So hydrogen and helium, they show positive deviation. And for other gases like heavier gases like nitrogen, methane, at first they show negative deviation, but again shows positive deviation. Nitrogen, even for methane, it shows slight negative deviation, and then it goes up away from this equation. And deviation of gases from ideal behavior can be given by, or can be measured by using compressibility factor. So what is compressibility factor? Compressibility factor, and this is denoted by the letter Z. So the compressibility factor is nothing but the ratio between PV real pressure volume of product of the real gases over the pressure volume of the ideal gas. So, and there are some assumptions of this compressibility factor, and those include like when these two are equal, same, that means it's ideal. That means Z, or compressibility factor, is 1, and it is for ideal gases. Ideal gases. But when our compressibility factor is greater than 1, it means at all pressures for positive deviation is for hydrogen and helium. Hydrogen and helium. And compressibility factor less than 1 at low pressure for all gases, and the compressibility factor is again shows positive deviation at high pressure. At high pressure for all gases. The compressibility factor shows positive deviation because at high pressure, when the pressure is very high, the gas molecules are being compressed, and so they experience repulsion. Since we know that same charges, they repel each other, so all the gas molecules, when they are confined closer and closer, we experience repulsion. The gases experience repulsion. That means, therefore, at high pressure, the compressibility factor is always, or it shows positive deviation. Now, this deviation from ideal behavior was to a certain extent corrected by van der Waal. By van der Waal, a Dutch scientist who was working with gases. So what are the corrections that he made in the gas equation. So we know that inside a cylinder, when we have a lot of molecules, there may be some of the, due to dipole-dipole interaction or London dispersion forces, they may attract. So during this attraction, speed during collision will be reduced because of the attraction, or momentum will be less, or force applied may be less, pressure may be less. So all these assumptions shows that the ideal pressure will be equal to P plus some correction. So what are those corrections? So the correction term, what van der Waals included was an squared over v squared. So here n is our number of moles, v is the volume, a is a constant or constant of proportionality. So this is our attractive forces, if there are any. So our ideal gas equation will be now P plus an squared over v squared, and the volume, number of, there may be repulsion, so he subtracted the number of molecules that has repulsion into nRT. So this is the modified form of ideal gas equation for real gases by van der Waals. See, this is BV is equal to nRT, but here we have some attraction, and here we have some repulsion. He subtracted some repulsions and included some attractive forces. So that's how he modified that gas law, van der Waals. So that's about it for this chapter. We'll try to solve some numericals. So here's our first question. To increase the volume of a gas by 10%, the pressure of the gas should be what? Should be whether it has to be same or increase or decrease. So we know V1 is equal to V2. If V1 is equal to V, V2 is equal to V plus 10 over 100. V is equal to V plus 10 by V, 10 by, oh sorry, 100 by, V by 10, which is equal to 11 V by 10. Now, P1V is equal to P2 11V by 10, or P2 is equal to 10 by 11V1, which is equal to 0.9V1, which is equal to 90%. 90% of P1. Therefore, decrease in pressure is equal to 10%. So you can try this too. If you have difficulty, you can ask me. So that's about it for this chapter. Because the liquefaction of gas, the liquefaction, uh, the liquid part has been omitted in your syllabus. So I think that will be good for this chapter. We'll still be doing that is be it for this midterm, but we'll still be doing other chapters.